Grazie per l'introduzione molto gentile, Vincenzo. Vi parlo da Pasadena, per i terrapiattisti, il lato sinistro del mondo. Oggi parliamo di AI per ecologia e vorrei cominciare dal campo che mi ha sempre interessato, che è quello della visione. Abbiamo un'immagine e senza fare troppa fatica la possiamo interpretare. Ciascuno di noi ha un'idea in mente di cosa sta succedendo in questa immagine. E la visione mi ha sempre affascinato perché è un senso così utile e così complesso, in cui senza toccare nulla riusciamo a ricevere dei fotoni sulla retina e a calcolare una visione del mondo, un modello del mondo che è abbastanza utile ci permette di operare ed avere successo nella nostra vita. Cos'è la definizione di visione? Quindi, cioè, la definizione più semplice che io abbia visto è questa: to know what is where by looking. E queste parole sono molto importanti. To know è la parte cognitiva, quindi avere questo modello in mente e sapere cosa succede. E poi ci sono quelle due parole, what e where, che sono what è che cosa, quali sono gli oggetti, e where cos'è la geometria, by looking, quindi ricevendo questi fotoni sulla retina. Il funzionamento della visione è sempre stato affascinante fin dall'antichità. Troviamo tracce anche in Lucrezio, e non so quanti di voi hanno tradotto il De Rerum Natura in scuola superiore, ma Lucrezio pensava che per riuscire a vedere senza toccare, percepire il mondo senza toccare, bisogna che ci sia qualcosa che si stacca dal mondo e ci entra negli occhi, e quindi un po' aveva avuto l'intuizione del fotone, e per lui erano delle sottilissime pelli che chiamava simulacra, che si staccavano dagli oggetti e nuotavano nell'aria o nell'etere per raggiungere i nostri occhi. E allora, per illustrare quello che succede, noi guardiamo il mondo, abbiamo una certa prospettiva sul mondo, riceviamo questi fotoni e siamo in grado di raggiungere certe conclusioni. Il punto di partenza sono questi fotoni che raggiungono la retina, i fotorecettori della retina li contano in qualche modo, e quindi partiamo da una matrice di numeri e arriviamo a dei concetti. E quindi questo problema, quando io ho iniziato a lavorare nel campo, non si capiva bene come poterlo risolvere. E vorrei notare che inizialmente nel mio campo ci siamo focalizzati su questioni di geometria, e queste questioni erano già state aperte dall'epoca del Rinascimento, dove Brunelleschi, Masaccio, Leonardo, Piero da Francesca erano stati molto interessati nel capire come si formava un'immagine e in che modo la geometria tridimensionale del mondo viene mappata, riflessa su una superficie piatta, che può essere quella della nostra retina del, o la tela del pittore. Nel caso di Lucrezio e anche nel caso dei pittori, si parla dei primi passi della visione, quindi il modo in cui la fisica e la geometria portano informazione del mondo sulla retina, però poi rimane tutta la questione della decodifica di questa informazione, e oggi vorrei focalizzarmi sulla categorizzazione illustrata da queste immagini. Naturalmente vediamo degli uccellini, alcuni di noi riconosceranno la specie di questi uccellini, vediamo un fiore sulla destra, alcuni di noi riconosceranno la specie del fiore, poi vediamo un pezzo di muro, un pezzo di vaso e così via. Quindi qui stiamo categorizzando gli oggetti che vediamo, e voglio ricordarvi di nuovo che l'informazione da cui partiamo sono dei pixel oppure dei numeri che vengono catturati dai nostri fotorecettori, quindi una matrice di numeri che è in qualche modo omogenea, e pian pianino il nostro sistema visivo riesce a decodificarla in concetti. E quindi questa è un po' la domanda, e oggi appunto mi focalizzo sulla categorizzazione. Quando ho iniziato a lavorare in questo campo negli anni 80, i tentativi di categorizzazione erano fatti un po' così, come vedete a sinistra. Qui c'è un modello di Fischler e Schlager per cercare di capire come catturare l'informazione delle facce umane dalle immagini. E come vedete, la loro idea è che una faccia è una composizione di elementi: i due occhi, i capelli, i bordi,
Pietro,
il destro e il sinistro, la bocca.
Pietro,
Sì?
Scusa se ti disturbo, ci sono un po' di studenti internazionali collegati e quindi forse potremmo passare all'inglese.
Ma molto volentieri, per me è molto più
Vincenzo, è un
facile.
problema?
Per me no, anzi per me è più facile e vorrei sapere dagli accademici se va bene.
Ma io sono d'accordo, vorrei sapere i colleghi che mi precedono se fa parte delle possibilità, se possiamo concederlo, se siete d'accordo, mi sembra di capire, Riccardo sicuro, vorrei sapere da De Concini se possiamo andare avanti in questo modo.
Perché nessuna istruzione, hanno parlato anche soci russi, americani, cioè,
Benissimo.
Va bene, questo
Allora,
Solo
allora
perché ci sono degli studenti che seguono in gruppi e alcuni di questi sono stranieri, per cui sono tutti nella stessa
va
stanza.
bene, allora go ahead.
okay, so we switch to
Please,
English.
please go ahead and good evening. Without, okay, you can enter in medias res, using Latin.
Okay, so this is the first attempt at capturing categories in computer vision. And here you see a model on the left where the idea is to capture the concept of a face. And so we decompose a face into eyes, nose, mouth. And we have the idea that these components have to be in a certain spatial relationship. Which cannot be rigid. It has to be somewhat flexible. And so you see those springs. And so for a while, people worked on probabilistic models that could capture the elements this way. And there are two difficulties with this idea. The first one is that in practice, it didn't work too well. And the second one is that, as we will see later, there are millions of categories that we want to capture and want to see. And it's unlikely that we will have enough people on the planet to build detectors for each one of these categories. So it doesn't scale well. So we have to find a better way. And towards the end of the 2000, it became clear, at least to me, that the right way to go was through machine learning, namely define categories through examples. And here on the left, you see examples of pedestrians, which are collected for a project on car driving, car safety. And once you have enough examples, then hopefully you can train a machine to find more of those. And so you would have something like this, in which having trained the machine, it's able to find a person, and then having trained it on examples of cows, then it can find cows and so on. And so the question is left of how to get enough labels to do all the findings. But if we can develop learning algorithms that are able to capture this information and then use it, then we are in good shape. And so this was a new approach towards the beginning of the 2000s, and one that I started becoming curious about. And so here you see more examples coming from different data sets, some of which we collected and some collected by other teams, specifically for pedestrians. We're curious to see how far could we go in detecting pedestrians in crowded scenes, and it looked very promising. And so we invested more in this direction. And so I want to be clear about the difference between getting AI by design versus learning. And so on the left, you see that a user might be a car company who wants to detect pedestrians, asks an engineer to develop by hand some pedestrian detector. That's the old style. And the engineer has to be very skilled because they have to understand what features are there that allow a machine to detect pedestrians. But the learning approach is different. So the engineer builds a generic learning engine, and we will go and see later what this looks like. And the user provides data and labels. So the user is in charge of defining the task through examples. And so again, images of pedestrian, for example, and the engineer has only provided the learning framework within which this can happen. Okay, so the question is, so it's clear that users can collect data and labels, and the data can be of various kinds. It could be pathology examples, it could be birds, as we will see later, it could be pedestrians or anything else. But the question is, what's the right learning approach that will actually work? We'll be able to learn from this data and deliver a working system, and which I call AI here for brief. And it turns out that now we are convinced that deep networks may not be the ultimate, but certainly is an approach that works really well. And I want to give you a quick introduction to how deep networks work and why do they work so well. And the idea starts in the early 60s from the work of visual physiologists. And here I have the pictures of Wiesel and Hubel, who won the Nobel Prize for their work. In the early 60s, they had developed good amplifiers that allow them to stick an electrode in the neurons of the brain of animals, and it was cats for Hubel and Wiesel. And they started being able to understand how the neurons in the primary visual cortex of the brain, how the neurons would code for information that was there in images. And they realized that in the early parts of a visual system, it's only very simple properties like edges or transitions from the light to dark that get coded. And so with time, people developed the idea that maybe the brain arrives at a very sophisticated point of perception, namely figuring out what is out there by looking, through a sequence of very simple operations, which are all similar one to the other, because the architecture of visual cortex and cortex in general is very similar throughout. And you see long hierarchies of neurons that communicate one to the other and progressively elaborate what information is there in the image. And so this was picked up by computer scientists in the 80s and 90s, and there is a long history. And here I'm compressing it down to one slide. So the point where we saw that there was something practical was the work of Yann LeCun, who developed a computer system called LeNet to read handwritten digits. And as you can see, handwritten digits can come in many forms. This was a competition put out by the US Post Office, who wanted to automate the process of reading zip codes. And the winning approach turned out to be a learning-based approach. And it was this network that you see down here that starts off from the pixels of the image. And then it has many layers of neurons, each one of which carries out more or less the same operation, which is, as we'll see, sums and so products and sums, and then some simplification. And it arrives at an output of 10 neurons, each one of which is specialized in recognizing one of these digits. And the crucial point, so there were two ideas here. One was how to set up this architecture, but the second one was how to train it, namely how to make it do what you want it to do from the training examples, which are a bunch of 50,000, in fact, digits that are labeled. And the crucial point was basically realizing that in the network, you have an enormous number of parameters. We'll see later how many parameters there are in these networks. And so you need to change these parameters until the network works well. So the network is generic. It could classify mushrooms or digits or anything else. And the choice of parameters is what determines what the network does. So the architecture is constant, but the parameters decide what the network is going to classify. And in order to choose the right parameters, a number of people, including Yann LeCun, realized that the simplest possible idea, which is Leibniz rule, the chain derivative, to minimize the error of the network was the way to go. And this takes the name of back propagation in the deep learning literature. And so this very simple idea, which involves complicated calculations, but not too complicated once you understand them, became very popular. Although at the time, people like me thought this is just a little toy because it only can tell handwritten digits apart, you cannot tell dogs, cats, and birds and horses. Those are too complicated. You could never do it, right? Okay, so now I want to explain to you how this network works, and I'll do it. And so I'll take a little detour, maybe 5, 6 slides, but hopefully at the end you will have a good intuition for how this works. So I'll start from a simple example. And by the way, feel free to interrupt me at any time if you have a question. So if anything isn't clear, just stop me. Okay, so let's suppose that we are in the office of a veterinarian, and we are taking care of cats and dogs, and we take measurements on the cats and dogs. And for the moment, let's focus on just 2 measurements, the weight and the length of the animals. And so a number of dogs come in, and we can take their measurements. And so we have Chihuahuas down here. They're very short and light, maybe 2 kilos and 20 centimeters. And we have Great Danes out here, longer than a meter, maybe 80 kilos, something like that. And so we have data on dogs. And now we take measurements of a few cats. And the cats are more slender. And so for the same weight, the cats are a little bit longer, and they're also a little bit smaller. And so the green dots illustrate the number of measurements of cats. And so you can see that the weight and the length of the cats and the dogs are somehow separate on this plane, so much so that I can put a line that separates the two. Now, that line summarizes in some way my knowledge on how to discriminate cats from dogs. And so if somebody gives me a mystery animal here, it's that point here, and asks me, do you believe that that's a dog or do you believe that it's a cat? I will say, well, from the data I have, it looks like it's a dog, right? That's my best guess at this point. And I can make the guess forgetting all the blue points and red points, just remembering this red line that have fit, and it separates well the blue and the green points. Now here, I drew the line by using my visual system. I just drew it in the middle. It works well. If I was in a high dimensional space, I wouldn't be able to see the line. And so I have to use backpropagation, so that algorithm I told you about, in order to fit the line and find its position. And so we'll see a little bit later how that goes. Okay, so now I have built my classifier. And if I have to give it to a computer, I have to give an equation to the computer that describes the line. And it turns out that the most convenient form is this one: S equals AX1 plus BX2 plus C. And so X1 is weight, S2 is length, X2 is length. A and B determine the position, and C the position of the line. And in fact, this equation tells me the equation of a plane in 3D that passes through the plane in 2D, and the 0 of S is equal to the line. And so if S is positive, then I can say I have a dog. And if S is negative, I can say I have a cat. So there is this sort of plane in 3D slicing the plane of X1 and X2. And the 0, the crossing of the 2 planes is the line. And so when I have, again, a positive S, it's a dog, and negative S, it's a cat. And so I could build a very simple mechanism to classify dogs and cats. I take the weight, I take the length, I multiply the length by A, I multiply the weight by B, I sum them, I add C, and I have S. And now I have only to decide if S is bigger than 0, in which case I assign to the output Y a 1, or smaller than 0, in which case I assign the output a 0. And so this is like a thermostat, it's a nonlinearity. And Y will tell me if it's a cat or a dog. And so if I get a cat, I will get a 0 out, and I know that it's a cat. And if the input is a dog, I will get a 1 out, and I know it's a dog. Okay? So this is a classifier. And what if I had more measurements, like the length of the teeth, the length of the hair, the smell, whatever it is? Well, I can just add more dimensions at the input, and I can add more weights to multiply these dimensions, and I sum them again, and then I pass everything through a 0-1 nonlinearity, and I get a classifier at the output. So that's very simple. And this object, I close it into a box in order to make it simple to draw. And I just summarize it this way. I have a vector of inputs x, a single scalar binary output y, and the behavior of this box, which I call perceptron, depends on those weights that multiply the inputs. So this perceptron is this generic box that allows me to draw a line through the plane and classify points left and right of the line. Okay. Now, let's suppose that we have more animals to classify, and let's retain the cats in the middle of the green, but then I have dogs, I have snakes, I have hamsters, and I have points all over. And you see right away that if I wanted to classify the cats, I'm in trouble now because a single perceptron will not be able to separate the green dots from the blue dots. Okay, so it looked wonderful, but in fact, it doesn't work too well for this case. And so how can I rescue the situation? Well, the idea is that I can use multiple perceptrons to create a box within which I can enclose the cats. And if all 4 perceptrons give me a positive value, then I know that I have a cat. If one of them is is 0, then I don't have a cat. Okay? So how could I tell a computer to carry out this operation? And it turns out that it's quite simple. So notice I have these 4 perceptrons, A, B, C, D. And now I have to compute a logical operation, which is an AND operation. So if A and B and C and D give me 1, then I have cats, right? So the way I do it is, again, I have these little boxes, A, B, C, D. They all take the 2 length and width. Each one of them computes some bit. And if I multiply each one by 1 and subtract 3.5, I get this AND operation from another perceptron. And so you see that just by adding one more perceptron that takes the input of the previous ones, I've been able to handle the more complex operation. This is wonderful because like the brain, like we suspect the brain is doing, through very simple operations, which are those little boxes, by concatenating them, I've obtained a more complex classification task. Now I can make it even more difficult. Suppose I had 2 groups of cats, maybe the house cats and tigers, which are also cats in some sense. And so the tigers are bigger, so they're separate groups. And so how could I say that anything green is a cat? Now, the previous method doesn't work well any longer because it could only classify a convex set. But here you can see that there are 2 convex sets, and so you can draw 2 boxes around them. Or even if I had this more complex arrangement, I could draw boxes that encapsulate the green points. And now what do I have to do? Well, what I have to say is that if a point is in either one of the 4 boxes, and so I have an OR operator, if it's in the first or the second or the third or the fourth, then I have a cat, right? And so how can I do that? Well, I add one more box. And so before we had the primary perceptrons that did the lines, and then I had the ANDs that did the convex sets, and now I have an OR that patches together convex sets, and I have a perfectly general classifier. And it turns out that even the OR operation can be implemented by a perceptron. And so if you play around with the weights, you can see how to do it. And so again, with these very simple perceptron boxes, I can obtain a universal classifier that can classify anything I want in principle. Now, what if I wanted to classify multiple species like dogs, cats, and mice? Well, I just add multiple outputs, each one of which is supposed to give me a 1 if the corresponding species is present, and a 0 if it's not present. And so in this case, I want to have a 1 here for cat, right? So now I can take each one of these different layers and put a box around it. And I have a sequence of boxes, each one of which has weights inside. And the weights determine what the box is doing. And the more boxes I put, the more general and flexible my machinery becomes. And so now I have a multi-layer perceptron, or a deep network, which is what people use nowadays to detect your face on an iPhone or classify objects in images. And so notice that the weights are matrices now, matrices of weights. And so I can have many, many weights. And the information is coded initially in the pixels of the image, which is a vector x0. and then the activations of the units in these different boxes, which are vectors x1, x2, and until the vector xl, which contains the code for which species is it that I'm looking at. Okay, so you may not have followed all the details, but you've seen how a concatenation of very simple operations, which are products and sums, and basically it's multiplications of matrices by vectors followed by elementary nonlinearities, can give rise to a fairly complex and rich set of behaviors like classifying objects in images. Now, we don't know yet if it works in practice, but the principle, I hope, is clear. So let's go back to visual categorization. And so here, let's go back to the early 2000s when I was starting to think about this question. And the more I thought about it, the more I was fascinated by it, but also the more I realized that it was not well defined. It was very difficult to exactly say what visual categorization meant. So in this picture, so we know that we want to say that there is a boy and he's reaching out to a cow and there are some nice mountains in the background. This is clear. But if we wanted to give a full account for what we see, well, we see also two small cows in the back. And so do those count as cows? Yeah, of course they count as cows. But do we see the horns of those cows or the hooves? Well, we don't see the parts of those cows. And so how can I hope to classify fully a cow if I don't see the different parts? And also you can see big trees in front, but there is a forest in the back. And so when is it that I say tree and when is it that I say forest? And do I have to count every single blade of grass on the ground? And if I see the mountains on the back, what counts as a single mountain and what counts as a group of mountains? And how should I think about it? And what about clouds? You know, is there a cloud or multiple clouds? How do I count them? And so the more I thought about it, the more confused I got. So at the time I was working with a very talented student, Fei Fei Li, and we started having conversations about this. And so I proposed to Fei Fei that we should simplify our life and create a data set containing 100 categories where we would have a bunch of images per category. And that would be our definition of visual categorization for now. And so we said, okay, it may not be the final definition of categorization, but at least we can start and we can see if we can build algorithms that can classify images for the category that we have assigned to them. And so we had a bunch of Caltech students download images from the internet. At the time, Google had just opened up and Google was indexing images. And so that was the first time that we could download enough images to create a data set containing 101 categories. And so that was called Caltech 101. And it made an impact because our computer vision community started becoming interested in visual categorization because all of a sudden they had something concrete to work on. And so the community switched from working on geometry to working on visual categorization. It was a very good thing that we did, putting out this data set. Now, Fei Fei became a professor, first at Princeton, now at Stanford, and she believed in this project and she kept going. And she collected a much larger data set called ImageNet, and which she finished by 2009. And this was 1,000 categories and 1 million images, about 1,000 images per categories. And her goal was to inventory the visual world by having images for each one of the possible visible categories. And so now she has about 30,000 categories in ImageNet, but somehow the 1,000 category subset became quite popular, and the computer vision community started working on this. And in the meanwhile, computers were getting faster. This is a depiction of Moore's law, where we double the number of transistors on chips in microprocessors every 2 years, and eventually in the in the 2010s. NVIDIA, which is a company making chips for video games, came out with very powerful computers for computer graphics. And so this was for boys who waste time playing video games at home. And lo and behold, though, the architecture of these NVIDIA machines was ideal for deep networks because they are optimized for taking products of matrices and vectors. And all of a sudden, we could do the calculations that we wanted to do about 1,000 times faster than we had been able to do them before. So many things became possible. And Jeff Hinton saw this opportunity, and he recycled the LeNet architecture of Viene, made it much bigger, and trained it on ImageNet, Fei-Fei's collection, and something magical happened. By the way, Jeff got the Nobel Prize in Physics last year for his work on neural networks, so that was a good thing. And so we had this confluence of three things that had been waiting, each one of them to become useful. And so we have the deep networks that I illustrated before. Down here, we have the NVIDIA GPUs, the chips that can compute matrix vector computations very fast. And we have ImageNet. And what happened was that in 2012, we had a dramatic improvement of the performance of algorithms that try to classify ImageNet. So before, we had about 30% error rate in classification, and all of a sudden, the Toronto team led by Jeff Hinton halved that error rate down to about 17%. And then very quickly, within 3 or 4 years, people working on their idea managed to bring down the classification rate to 5%, which is more or less the level of ambiguity of the data set. So you cannot do better than that. And so the computer vision community had been struggling to get 70% correct, so 30% error, and all of a sudden, boom, we get down to 5% very quickly. And so it became evident that these deep networks could do amazing things, and everybody became interested in them. And that's somehow what sparks the current, let's call it AI revolution. It was the confluence of ideas from neuroscience and the deep network algorithms, and then large annotated data sets that we helped bring about, and then VLSI, faster and faster microprocessors, and then GPUs, and all of them together created this opportunity that we are studying now, which is what people call AI. Okay, so now back to visual categorization. And so now we had some interesting mechanism, deep networks that could be trained by learning. And the ambition we had was enormous. So we have, as we go about our lives, we have many puzzles that our visual system gives us. What kind of a bird is this? What kind of a script is this? Who wrote it when? What does it say? Is a mole on my lip, is it pathological or not? Do I have to see a dermatologist about it or not? Who is this Roman emperor? What kind of a tree is this? So we look around and we have all sorts of questions. And so we would love our machines to be able to help us solve these questions. And so the question that we're asking ourselves as computer vision scientists at the time were, how many categories should we work on? Is it 10, like the handwritten digits, 100, 1,000? How many categories are there in the world that we have to consider? And how many training examples do we need for our machines to become proficient at classifying these categories? Can machines do fine-grained categorization, like the fine distinction between two species of birds that are similar to each other? And who needs visual categorization most? Which kind of data should we work on to give maximum benefit to society? And the last question is, how can machines learn? Because initially, it's us computer scientists collecting training examples like the digits, that's easy, or the pedestrians. Anybody can tell what is a pedestrian. But the more interesting problems have to do with, again, pathology or radiology or birding or cell biology, where only experts know the truth. And so we have to be able to build machines that can learn from experts, and experts are very few and they don't have time. And so how can we have this transfer of knowledge from communities of experts in the world to a machine that can help us? And so I want to go very quickly through these questions and then give you some examples of what we can do. So first of all, it's clear that there are lots of different categories. So we have all the people in the world, 7 billion. In principle, you would like to recognize them all. Chinese characters that are tens of thousands, types of shoes and belts and cell phones and automobiles, even man-made objects. There are millions of different man-made objects. We have the family tree of all living things. Again, millions of different species. So it's clear that we go from millions to billions very quickly. And so the ambition is gigantic here to be able to recognize all of these things. And indeed, fine-grained categorization cannot be easy. And so here I have just a few species of sparrows. And if you move your eyes across this page, you see how similar they are and how difficult it is to keep them in mind and recognize them all. How do you do it? And then, so at the time I was talking to a colleague, Serge Belongi, and saying, well, we have to find a community of humans that needs categorization and with whom we can work so that we can build a machine that can learn from the community their knowledge. And so what kind of people should we work with? And somehow I started getting ideas from interactions with my father-in-law, who one day sends me this picture. He was taking a hike in New York and saw mushrooms, and he remembered that I like to pick up mushrooms on the Alps, and he thought maybe Pietro knows what the species of this mushroom is. And so he sends me this picture from his iPhone, and he says, well, can I eat this one? And so I look at it, and I think right away, no, this is not the right mushroom to eat. I didn't quite know the species. So I reached out to a cousin of mine and asked him, what do you think this is? And so after a while, we decided that it was an Amanita pantherina. And if you look it up on Wikipedia, it's poisonous. So I told my father-in-law, no, don't quite eat this mushroom. And it was a curious example because my father-in-law is very technologically oriented. He has an iPhone. He could look it up on Wikipedia, but there was some missing link in which, to look it up on Wikipedia, you need the words, Amanita pantherina. But here he has an image. And so tying images to words and giving species of animals and plants seems to be a very useful thing to do, and seems to be useful to give people the ability from their iPhone or their smartphone to classify any species of plant and animal they see. And so we thought if we aim to do that, then we'll have lots of people who give us lots of images, and then we can study how many classes are being discovered, how many species, and we can get lots of training images. We can study how good are our machines at doing this and all of that. And so the idea was, well, maybe you look out at the environment, you see something you're interested in, you point your phone, you take a picture, and the phone gives you a species. Okay, this is it. This is the task that we want to resolve. And we were lucky enough to find two communities of people who had started trying to do this, but only through human power. And so Merlin Bird ID and iNaturalist. So Merlin Bird ID is the app on the left, and it was created by the Cornell Lab of Ornithology. And iNaturalist is originally from the California Academy of Science, another app that allows people to take photographs. And initially, people would post the photographs on a social network and hope that some expert would come along and help them classify the animal or plant they had seen. And so the need was there, the community was there, but the communities were not prospering because there were not enough experts. And so this is a crucial point that we realized was very important, namely the experts are very few and far in between, and they don't have time to help people who are beginners. And so the experts are only interested in hard problems and not in trivial problems, and they don't have the time to go out and help people classify birds and plants and animals. And so we thought that's ideal because our machine can learn from the experts, and then it can resolve all the easy cases, and it can leave just the difficult ones for the experts, which is what the experts are for, right? And so one of our students, Grant Van Horn, embedded himself in each one of the two communities and implemented two things. One was a deep network for recognizing plants and animals, which was using the data that these communities had already collected as a training set. And the second one was a statistical backend that would work out which experts knew about which class of objects so that we could have safety in assigning labels to these different species. And I'll give you a little bit more details in a moment. So just to show you what one of these communities look like, this is iNaturalist, and the hotspots show you where people are most active in collecting images. And so it's a worldwide set of people. And the more they collect images and they label them, the more our algorithm can learn from them. And let me demonstrate to you how it works. So by the way, I encourage all of you to download to your phone both iNaturalist and Merlin Bird ID. And I will not describe it today, but Merlin Bird ID can recognize birds also from their sound, and it's a lot of fun to do so. So you should definitely try it. Okay, so here is a picture I took in Oregon maybe 3 years ago, and I wanted to know what fish was this, and so I use iNaturalist to tell me, and iNaturalist gives me 5 suggestions and different species of salmon, and then catfish, and so on. And I know that usually the top choice is the correct one, so I clicked on the top choice, and I committed to that, and it posted my image, so Chinook salmon, and now 3 people came along and confirmed my identification. And so you see that now the iNaturalist has enough evidence, 4 people agreeing, that it decides that this picture is research grade with this particular label, Chinook salmon. And so it can use this picture to train itself. And so the next time somebody uses it, it's even better than before because it has more training examples. Now, do people always agree? And it's not the case. So here is another picture, and I used the system and decided that it was a cutthroat trout. And I don't know how the name in Italian, so I'm sorry about that. And but now you see that the system labels me as improving, which is a euphemism to say that I don't know much about fish, so it doesn't trust me. Somebody else comes along and says, no, it's a rainbow trout here. Now, this person is labeled as a maverick, which is even worse. It's somebody who is truly injecting noise in the system. And so it doesn't believe this person either. But then 2 more people come along and they have high reputation for the system, and they say cutthroat trout, and now it gets the approval and becomes research grade. Okay. Now, here is another example. So this was in the province of Venice last summer, and I see this beetle, and I decided it must be Mediterranean spotted chafer. But then I am a maverick even here. I don't know anything about Coleoptera, so of course the system doesn't trust me. And 3 people, 2 of whom are trusted, are willing to commit to the genus, but not the species. And so now the system only knows the genus, but not the species of this image. And so the system is not sure yet, and it's a 2/3 probability for assigning a label, and it's still waiting for 1 more expert to give an opinion. And so this is not part of a training set yet. Now, the last example I want to give you is amusing. So I was walking near Massachusetts, this was 2 years ago, and I see this tree that is missing all the leaves and has been chopped down. And I think, oh, maybe the system can recognize the tree from the bark. So I take the picture and I ask it what it is. And so can you guys guess what the system said? I'll give you a second to think about it. And so now let me reveal what it says. The system says that it's a beaver. And so why would it say that? So initially I thought this is crazy. But then I realized I looked at the cut marks here, and this is clearly the pattern of a tree that has been cut down by a beaver. And so enough images are present in the system labeled beaver that look like this. And so when the system sees a chopped tree with these tooth marks on the top, it says, well, the thing to say is beaver. Okay, so from this you understand that this system is being trained by the community. And if a community decides to use a certain label, that's what the system will do. So this way, it can also recognize footprints of animals. It can recognize the scat of animals. and different signs, including this one, and associated to different species. Okay. So how can the system figure out whom to trust? And so here I have to speed up a little bit because we want to be done quickly. And so there is a statistical model, which I will not explain, but it models what is in the head of the annotator, so parameters that are in your head when you decide that this is a beaver or this is a beetle, and parameters that are intrinsic to the image. And here they come together, and the annotator generates a label, which is a species label. And the system only sees the species label, but it turns out by inferring what is in your head, by looking at what you do on many images, it can guess how much noise is in your head, how accurate you are, and what are the criteria you use for classification. And so this allows the system to decide how much it should trust any member of the community. And so this turns the table a little bit on machine learning. It's not an expert that tells the system what to do. It's a system that has to develop a social network and has to develop trust in the different experts and has to decide for itself what is each piece of information meaning. And so I have an example of this here, which I will skip in the interest of time. And I want to get to the last little bit. So this iNaturalist network, after we became involved down here, has become huge. It's now about 4 million observations per month. These are the statistics we get now. So we have now 300 million observations that we have collected and about almost 10 million users, and of which maybe 400,000 are active, namely 400,000 are labeling, are providing labels for the images. And so with all this data, we can answer some of the questions I put up before. For example, how many training examples do we need to be accurate? And this is a small example put together by my student, Sarah Beery, who is now a professor at MIT in AI for ecology. And what you see here is the error rate of one of these classifiers as a function of how many training examples there are per class. And so there are some good news, which is with enough training examples, the error rate can come down to more or less 1%, which is very low, much better than humans, because the images are often quite difficult. And the bad news is that you need lots of images to reach that level. So 10 to the 4, so with 10,000 images, you can reach 1% accuracy. But if you have only 100 images, then maybe it's 10%. Error rate, right? And so this is where we are with the current technology, and of course we want to improve it. But the system works well, so you can enjoy using iNaturalist. Now, from iNaturalist, since we have 300 million observations, we can also estimate the distribution of species around the globe. And so for the first time, using this kind of data, we can estimate worldwide distribution of about 100,000 species. So in the years through use, the number of species that iNaturalist can recognize automatically has gone from 5,000 to 100,000. And so we can carry out these estimates. And again, I will not give you all the details. It's a difficult problem. And the difficulty is that the data of iNaturalist are only positive, not negative. And so here, maybe the image will be classified as Amanita pantherina, but there are other species around that don't get a label. And so how can the system work out from this very imperfect and partial data, the position of all the plants and animals? And it turns out that by exploiting correlations between these 100,000 species, you can learn a lot. And so there are some interesting mathematical maps called embeddings that we can infer from the joint distribution of all of these species. And we can infer many things, namely where photographers go, what are these embeddings that correspond more or less to ecological niches, and how different photographers behave. And from that, we can infer the distribution of species throughout the world. And this is work by my former postdoc, Ashim McKay, and student Eli Cole, who are now out and professors themselves. Okay, so I want to close here to give time for people to ask questions. And so I told you a little bit about supervised learning. I explained to you how perceptrons and deep networks work. And then I gave you an idea of how a naturalist and Merlin Bird can learn from a community of experts. So we have somehow freed the algorithms from the need to have an expert that tells them what to do, and the algorithms are able to socialize with experts who come in asynchronously and learn from the experts. And I showed you that using that kind of data, we can estimate the distribution of species on a planetary scale. And so these are my collaborators on these projects, and I'll be happy to take questions now.
Very, very good. Very good. Time perfect. Examples very catching. And behind the examples, an amazing development that has been accelerating over the years, as I understand. So, why people attending, which they are reasonably numerous, and so I'm convinced that you had stimulated some intervention. So the colleagues, students, attending people for different curiosities, you are all invited to ask questions to Professor Perona, and please go ahead.
Maybe I can just break the ice, if it is okay.
Bye.
So I had a couple of questions. One is, how are LLMs and diffusion models for generating images changing the scenario? Because you have talked about deep learning, let's say, in a classical kind of supervised setting. But then you have all this generative AI coming into play. Does this change somehow the framework that you are describing? This is the first question. The second question is that all these systems based on a huge amount of data are kind of intrinsically software system, in the sense that you cannot imagine a physical system, a biological system that works the same way. To start with, you cannot imagine to implement learning in the same way. So what is the interface with this kind of more biologically motivated models that perform similar tasks? So these are the two questions.
Yes. Okay, so in brief, so I didn't cover LLM and foundational models today. I thought I may cover them maybe next year or whenever I get to talk to you again.
Okay.
And it's an interesting development, of course. These systems are able to do more than supervised systems because they can now associate text and images in a much freer way. So you can obtain a whole sentence describing an image from an LLM. They are not yet at the level where they can classify in a fine-grained way plants and animals and or cancer in X-rays or whatever. And the reason is that they require more training examples because they are less supervised. And so here I was focusing more on fine-grained expert level categorization, which still requires supervised learning. But certainly they will eventually facilitate, because you can pre-train systems using an LLM, and then you can fine-tune them with supervised data. And so certainly they help. And the second question is, what's the difference between a naturalist that learns from interaction with a crowd through cameras that people carry around, and a physical system like a robot or that goes around and interacts with people in a physical way. And so, there are, or even an automobile, if you will. Well, and so there are pros and cons. There are, as you can see, a naturalist is perfectly satisfactory for what it has to do. It doesn't need a body to go around because the body is provided by millions of people who go around and have a good time hiking on the mountains. If you have to, so the example of autonomous driving is interesting because now you have millions of, say, Tesla cars with 11 cameras each, taking photographs whenever you brake, whenever you turn. And so those systems can train themselves and they can exchange data. And so they have an unfair advantage over regular drivers because a regular driver only has the benefit of a few tens of thousands of hours of driving, but these systems can share over millions of vehicles. And so they can see more things than any driver will ever see. And so eventually those will be much better drivers than we are. By virtue of sharing information easily. I don't know if I answered your question, but this is, and the strategies for learning, of course, have to be improved because it has to be lifelong learning. So the systems cannot learn once, they have to keep learning. And so we'll see how that goes. And that's an interesting topic itself.
Are there any other questions to?
Yes, please.
Maria Giovanna, please go ahead.
My question is, let's say from an engineering point of view, the problem just now is that the amount of calculations you need also for recognition, but in particular during the training phase, requires a lot of energy. So since in the title of your presentation you mentioned ecology, well, that's a bit against ecology.
Yes. Yes, yes.
Possibly, let me say, restricted learning environments for particular applications in which you can spend a bit less energy? Thank you.
Yes, so Maria Giovanna, thank you for your question. That's definitely a concern, and I think that the press has talked about in the last year or so. And I have taught my students how to compute how much CO2 are they producing with each one of their experiments. And it's quite interesting. So I can teach it to you or to all the people listening as well. So the GPUs that we use take about 1 kilowatt. And if you think of an automobile that drives from Rome to Venice, that's about 20 kilowatts for about 6 hours. So it's maybe 100 kilowatt hours type consumption. So driving from Rome to Venice is about like one of the experiments that we carry out, because it's typical experiment carry out is about 100 hours of compute. So this is like a this is the comparison. Now to train iNaturalist, it's more or less that amount of time. And so imagine one automobile driving from Rome to Venice, that's the order of magnitude for training iNaturalist, which is a lot, but whenever you have to, I'm sure that the members of the Academy who live in Padova and decide to drive to Rome for a meeting, they wouldn't think twice, right, to drive if that's the best way to go. So that's the level for these supervised models. Now, the unsupervised or self-supervised models, the LLMs, the foundational models, those take much more training energy. And so you have to multiply by about 100,000 or maybe a million the energy. So it would be like a million cars driving for, when you use ChatGPT, you should imagine that in order to train it, it was about, and again, it's sort of order of magnitude, about a million trips from Venice to Rome. Now, is that a lot or is it little? Well, if you think about the traffic on the freeway in Italy, it's maybe, it's maybe, I don't know, a week or a few days of traffic on Italian freeways. That would be which is a lot, but it's still not huge compared to all the rest of human activities. So it's something that we have to keep an eye on. I think that there has to be a justification for training these models. And since it costs a lot of money to train them, it's not going to happen unless there is a justification. And so I'm less worried than what the newspapers make us think about, but at the same time, it's something, of course, to keep in mind. And so thank you, Maria Giovanna.
Let's say I wouldn't suggest it for just fun.
Uh,
A bit expensive.
well, okay, so we can have a conversation about that. But thank you. Yes, thank you.
Thank you.
From now on, I don't see any hands wishing to ask you things. How would you believe whether we can go beyond the categorization at the same speed when we are considering the enormous amount of applications that emerge from information science in specific fields like, for example, drug developments and or any system determined by deterministic processes or statistical ones, and then lead us to decision more specifically, not only into classifying all possibilities, but essentially the transformation between them. How the transformation occurs, how can we follow it? Of course, this opens orders of magnitude of variance. Is there any model, any robust mathematics behind? As I understand, most of the activity of the mathematics that it is involved in all this categorization is of linear algebra, or
Yes.
how can we
Yes. So
what about transformations, continuous transformations? How can they dealt with?
So you're a chemist, so I think you have in mind, for example, how does one design molecules or proteins that achieve a certain goal, for example, how
chemists get Nobel Prizes for that.
exactly. So
Computer science, in computer
there was indeed a prize last year that was given to AlphaFold, Demis Hassabis,
exactly,
the Baker Lab in Seattle. And so it's very interesting. So let me talk about what Baker does, because I just saw him a couple of days ago, and I caught up with him on what he's doing. It's very interesting. So it all starts with an idea called diffusions, which allows you to synthesize images from text descriptions. And so all of us have tried on ChatGPT, and you can say, give me the picture of a boy fishing in a lake or whatever. And so you get the picture, right?
That's it.
And so there is this space, which is an embedding. It's an abstract mathematical space where images and text are described using vectors of about 1,000 dimensions. And now what happens is, if we specify text here, we can specify a target for an image to be like that text in some ways. And the diffusion starts from a completely random image, and it progressively changes it until it becomes compatible with a text description. And so this happened about 5 years ago, 2000. And in fact, there is another Italian, Stefano Ermon, who is a professor at Stanford, who is a co-inventor of this idea that is very powerful. And these diffusions that start from noise and progressively synthesize an image work with deep networks similar to the ones I described. And so you take an image and you modify it progressively, little by little, until it meets the standards of specified by text. You know, the chemists have understood that they can use exactly the same mechanism that was developed for text and images. They can use that mechanism for synthesizing molecules that have a certain function. And so they specify the function, and as I understand it, it's at the level of text or very simple ways of describing what the function should be. And the molecule is described by, and so here it's different representations, but you can think about the configuration of the different atoms in a certain configuration, including the cloud of electrons, maybe. And so the molecule is like an image, and the specifications of what the molecule should achieve are like text. And you code both in this embedding space, and then you start from a completely random molecule that is like a cloud of noise, and slowly it converges towards something that is useful. And the fascinating thing is that, like in ChatGPT, if you give the same specification 3 times, you get different images. Well, also for the molecules, you can get different molecules that have the same function. Of course, you then have got to test them in the lab to see if they work or not, because sometimes you just get something that doesn't work or is not stable or whatever. But it gives the chemist a nice starting point. And somehow these methods capture what chemists call chemical intuition, in which you have this intuition of how you should how you should shape your molecules. I don't know if I answered your question, but yes.
No, that's wonderful, because not only you focused my questions much more than I had in mind, and on the other hand, you gave me hints and illuminated me towards a very, very interesting perspective, so that I definitely congratulate you. I'm so glad and honored that you belong to our 40 people plus some additional ones. We are 40 plus something else. And I trust you will help us to develop further investigation of these topics, inviting people, organizing meetings on this. And so I really trust you to be illuminating other people besides me tonight, beside us tonight, for further progress. So simply let me announce that we will move next. We will move next November 27 at 11. At 11 towards another colloquium where we will have as a speaker Alessandro Melchiorri, astrophysicist, another addition to our academy, that being essentially a cosmologist, will help to look at the universe where we live in an interesting way. Grazie mille a tutti, arrivederci.